Okay, so this will be fairly informal. I'll give I don't know, there are about 10 slides, and you can interrupt when you like and ask questions. Hopefully, by the end, you'll get some idea of what's going on in Polar with respect to cyber infrastructure, and what are some of the opportunities for cyber infrastructure. And on some things, I'll be relatively vague because I can't say certain things about programs, solicitations that are making their way through. But I'll give you some idea about what's going on the bigger picture. So let me give you just a background. I am actually the Arctic Natural Sciences Program Officer. And when I came, Marco Tedesco, he was the program officer for cyber infrastructure, and the group didn't bring anybody new in. And I took over the program as sort of a de facto program officer for what's going on in cyber infrastructure. Now, I also so as we make our way through this talk, I'll try and give you an idea of, I'll be talking about the Office of Polar Programs, but I'll also be talking a little bit about EarthCube, which is GEO's cyber infrastructure. And then I'll also be talking about the Office of Advanced Cyber Infrastructure. So I am the de facto cyber infrastructure person in the Office of Polar Programs. I sit on the EarthCube committee, and I'm GEO's rep to the Office of Advanced Cyber Infrastructure for their solicitations. Okay, so what I'll do is, let me presumably I'm sharing the screen with you here. And what I'll do is this is an outline of where we're going. And, I don't know how long it will take. Maybe it takes 15 minutes. We can just leave the remaining time for questions, or you can interrupt as you like. I'll give you some sort of working definition. I'll talk about a few Polar projects so you get an idea of some of the things that are going on, some of the data centers, some of the physical networks. Talk a little bit about, we'll talk quite a bit about the funding mechanisms, and I'll give you some idea about the dollar values associated with those. Data archiving lessons, we can see what kind of time we have. And then I'll talk a little bit about the challenges that, questions that we're asking ourselves within the office about where cyber infrastructure is going. So I have a pretty crude definition of cyber infrastructure. And if you look at what's funded, you'll see what I mean. So I call it all of the computational stuff: algorithms, workflows, GPUs, machine learning, without which it'd be difficult or impossible to answer the kind of complex questions that we have. So really, I'm talking about all the computational stuff, and to some extent, even the hardware, where you think of, the supercomputing centers at Blue Waters or Texas, or, as part of NCAR. So all of that is what I'm defining as cyber infrastructure. And hopefully, as I make my way through here, it becomes a little clearer. And I'll start by showing you just a few of the awarded Polar projects. And not everything here is funded just by Polar. And that's something I want to emphasize as I go along, is that where the opportunities lie for Polar researchers to get cyber infrastructure projects funded. So I'll start off with, and like I say, these are already awarded examples of just a little bit of a range of cyber infrastructure projects. The first one is a career project by Wenwen Lee out of Arizona, and what she is developing is basically a front end where you can do searches, and the searches, let's suppose you're searching for permafrost. What it will do is it will crawl the web, and it constantly is doing this to some extent. And it's looking for databases, and it's organizing where those databases are, what kind of databases they are, and what formats they're storing their metadata. And so it's not telling you that here's an Excel file, and that Excel file is containing, I don't know, some ground temperature data or carbon storage. But what it is telling you is that if you're looking for this item, what it's telling you is where the 16 databases that you might want to go to and look. This is where the data exists. And it involves web crawling, it involves machine learning, and it's a supervised machine learning. And the second project is somewhat similar in a sense. So this is Chris Mattman's project out of USC. And what Chris is trying to do is he's not looking for the databases themselves, he's looking at the data that's in these databases. Or he's crawling the web to count the number of times something is mentioned. So this involves, again, machine learning. It involves text mining, web crawling, and again, it's supervised. It's supervised machine learning, and it involves, to some extent, and it depends on how big of an extent, both of these involve, but more Chris's, is the involvement of the domain folks. So it's not just, so when it looks for some data, you look at it and you say, yes, this fits my criteria of being data that was within my search. And then it will go again, and it will keep doing it until it's trained to really look for the correct data. So Wenwen Lee's is to look for the data sets, and Chris's is to go and look within the data sets. So the next one is a recently funded project, and this was funded out of, it's funded out of a lot of groups. It was funded out of Arctic, it was funded out of Antarctic, and it was funded out of EarthCube. And this is Heather Lynch's project out of Stony Brook. And what they're trying to do is they're taking the remote sensing data, they're doing image processing, they're doing basically they're doing object identification, again, a kind of machine learning, and they're moving this through a pipeline, a computational pipeline that goes from the remote sensing to a parallel processing pipeline to analysis to feature detection. And in this case, she's looking at many things. She's looking at feature detection for seals in Antarctic, or icebergs in the Arctic. So there are a lot of things that are going on in this project, and it's meant to do it completely in an open source framework. So basically they're coding in Python, in notebooks, using Jupyter notebooks. And so they're trying to do two things. They're doing their science, and they're creating a pipeline and a workflow where people can go from the remote sensing through the pipeline to whatever feature detection they're looking at and some analysis. And it's completely, so there's the scientific ambitions here, and then there's the community tools. And they're trying to create so all of this is basically, people store their stuff on the Arctic data center because that's one of our requirements, their metadata, but all of their codes are going on to GitHub and trying to make this a tool for the community. The next one is Irina Overeems out of Colorado. And what Irina did was really nice, and it to some extent combines supercomputing with sort of creating an interesting teaching environment. So when you log on to what Irina has, you have an interface, and this is she's looking at permafrost modeling, and the version I saw was basically what they're trying to do is calculate ground temperatures, and you can use those ground temperatures for whatever you want, and it could be melting of the soils, melting that's going on in the soils, or it can be for microbial decomposition and generation of CO2. But what it does is it takes you through a simple modeling framework. You can choose, the most empirical of thermodynamic models, and you can say, okay, I want to look. You'll choose a forcing data set that's got some, let's suppose, temperature and precipitation, and you choose a place that you want to do it, and you use this empirical model to generate a time series of ground temperatures, but you're doing it through the supercomputing center. So when you submit your job, you're submitting it through the use of their supercomputer. Now, doing it at a point really doesn't need a supercomputer, but if she wants to go to the more complex physically based models, and you decide that, oh, I want a grid of a certain grid size, and then so now I've got something that's going down in the Z direction, and I have a spatial problem in the XY direction. You can do all of Alaska if you want, and you'll choose your forcing data set, whatever gridded product you want, and you'll choose your, I believe, and I don't completely remember, you'll choose what time scale, that the delta T that you want to use, and you can force this model. And maybe this is a more complex physically based model, so it's not only have a temperature and precipitation, maybe it uses incoming solar, long wave radiation, and now you do have a problem where if you're doing this spatially over all of Alaska at a relatively fine grid, when you submit that job, now you do need that supercomputing center. And when your job is done, you can do visualizations. And so it serves a few different purposes. It's a really nice teaching environment on the one hand to take somebody through in a very simplistic way, submitting jobs to a supercomputer. But it's also a community tool for a researcher. If you're a little bit more savvy, you can even take her model, and again, it's on GitHub, and you can, you'd have to be a little bit more savvy, but you can take that and modify that model to what you want it to be. So, and the last one is is the Arctic Data Center, and they have a small supplement. And so the Arctic Data Center is the primary place where all metadata for Arctic funded projects have to go. And they brought that, so that data set has about 4,500 records, and about 2,000 of those records really have well-documented metadata. And so let's say the remaining 2,500 data sets do not. And so the question is, how do you recover some information from those remaining data sets? And basically what they're doing is they're using the 2,000 data sets that they have for training a model, again, a machine learning model that uses semantics. And what they're doing is they're using as ground truth those 2,000 data sets. And basically what they're trying to do once they have a trained model is extract more information than otherwise would be there from the less documented data sets. And so hopefully that gives you some idea of the things that are funded. There are other projects, such as taking Andy Schwanden's ICE model and bringing that on the cloud and trying to make that, in a sense, user-friendly and basically something where you can go straight on the cloud and run the ice sheet model. And obviously nothing is as easy as it sounds, but or doesn't sound, but so these are the kinds of projects. And the ones that you're looking at here were funded either in Polar or in EarthCube. And EarthCube, if for those who don't know, that it's a group that sits within GEO. It's a program that essentially is to act, to look across GEO and ask the question, what kind of projects do we want to fund that would help our geoscientists ask the questions they ask? What kind of cyber infrastructure, what are the bottlenecks in computing? Whether it's the workflow, the hardware, the software, what are the bottlenecks and what are the projects that we could fund that both have some, obviously they're working on a given scientific project, but they're also developing a tool that can be used within the geoscience community. Now, it used to be that in Polar, we had within the solicitation, we had a specific call for cyber infrastructure projects. EarthCube right now serves that function for us. We no longer have that in the solicitation. And what we say is that if you want to be funded in cyber infrastructure, we have the PI go and solicit to EarthCube. And so on Polar, I sit on that. And so the proposals are reviewed like any other proposals. They're sent out both on the computational side, and they're sent out for review on the domain side. They're reviewed like any other panel would review proposals. And the only difference to some extent is that for those projects that rank highly, in many cases we're splitting the funding between the program, the EarthCube program, and the domain. Either in us, it would be Arctic or Antarctic. So right now, all of these projects that you see here are funded from one of those two sources. So let me skip the data center for a minute and the networks. And I wanted to, let me go back. I removed the slide, but I want to talk maybe for a minute about So here are examples of awarded projects. I'm saying that they're funded through two different avenues. Well, through the domain, Arctic, Antarctic, or Earth Cube, but we don't have an explicit solicitation. You go to Earth Cube. Now, there is another funding mechanism, and some people have used it and other people's, many people within the polar community have not. In the larger geoscience community, they do, and that's the Office of Advanced Cyberinfrastructure. And they have solicitations. They have the big data solicitation, which is DIBS, and they have the SI squared solicitations. And those are for both data and software, okay? And they come out once a year. And for those who've been reading the Dear Colleagues letters, you've noticed there hasn't been an EarthCube solicitation for this year. We're putting that off. And the same has been said for the SI squared. However, people are working on things, and solicitations will be coming out. That should, that's an expectation. And so let me talk a little bit about this other place. And so EarthCube is just taking a break, actually, at this point. It's not stopping its solicitation. It's basically letting those projects that are currently funded evolve a little bit, and then we'll see and then next year, most likely, the solicitation will come back. But let me talk about this other avenue. And it's really a place that the polar scientists should see an opportunity. And that is in the Office of Advanced Cyberinfrastructure. And so like I say, was DIBS, which was a big data basically, and then these software, and they also had a software component and they have a data component. And the same sort of general, whatever cyber infrastructure, this definition probably works. Everything under the sun comes through there. Now, everything that comes through there has to have, the primary thing they have to be doing is looking at a science question. And then they have to say, there's a bottleneck, and that bottleneck is computation. Or that bottleneck can be something close to computation, something about optimal network design. But it is a cyber infrastructure. And again, it's a loose definition, and you have to sort of go on and see what's been awarded there for you to really get a fuller understanding of what it is that they're awarding and how you can fit in. But I will tell you, the way it works is as follows. Now, I'll say first, let me just, the total budgets in ANS for last year, whatever it is, 12, 13 million, same thing for Arctic System Science, something around there. DIBS and SI squared are talking around 40 million. So these are places that really have significant resources. Now, the way it works is there's a science question, there's a bottleneck, and then there's the solution to that. And typically these proposals will come in with a very strong computational side, and then, a science side. And they're usually multi-universities. They don't have to be, grants are somewhere between, 250 and a couple of million each one. The program officers who sit on those proposals are coming from all the directorates. And so I will sit there for geo. And so what happens is, again, proposals are evaluated in exactly the same way it is in other NSF programs. They're sent out for review to cyber infrastructure people, to computer science people, to the folks who are in the domains. They come back. They go into highly responsive, or not responsive. And then everybody who's looking at those for the directorates take back those mostly the highly responsive. They take them back to their directorate. And so I will take it back to the directorate and say, here are the 10 projects that are really ranked highly. Who has interest? And what happens is somebody will have interest possibly, and they'll say, I'd like to fund that. And the advantage to Arctic is that the funding is always split. So it may be that, I don't know, Arctic Sciences pays half, and then the Office of Cyber Infrastructure would pay half. And so there's real leveraging that's going on there. And so you could see to some extent why we think that our community should be submitting to these programs. Now, the polar community has submitted, not nearly as extensively as the physics community or some other communities. And so this is what I want to say, is that in the next, 2-3 months, solicitations might come out. And, these are, because they're larger pools of money, the expectations are that you have really well-integrated teams of people who are coming in. So if a solicitation comes out in the next couple of months, might happen, you only have 90 days. And so what I wanted to get across to people at AGU coming up is that there's real opportunities, and especially, hopefully coming out in a short while for the polar community to do things that they really weren't able to do in to some extent, our much smaller programs. So I want to, I was going to talk a little bit about polar data centers or the networks, data archiving lessons, but I think instead I'm going to just close off. And, for 5 more minutes, I'll talk about the challenges that we're looking at in polar, in cyber infrastructure, and the things that we sort of ask ourselves every day. And so I'll talk about 2 of them, data and computing. And so on the data side, well, we have the Arctic Data Center. And the question we ask ourselves is, how central should that data center be as a hub for software development? So there are 2 ways of going. One is to say, all of our data is flowing in there. The metadata looks really nice. People should be mining that data. Well, if they're going to mine that data, they're going to need some software developed. And so the question for us is that the responsibility of the data center to create software so that the community can come in and mine that data? Or a second option is to say, no, what should happen is that people from the community should be writing software that's being put into a repository that could easily access the data center. So there's a question for us. How strategic should we be is, again, when we fund a cyber infrastructure project, it is a little bit different than a normal, completely normal NSF grant. In an NSF grant, there's a lot of leeway for the PI, just tremendous amount. But in a cyber infrastructure, there's 2 things going on. One is you're looking at the science, And there's two, that there's a promise of developing community tools. And so we are always looking at these projects and trying to stay on top of them as far as saying, how's the science going? Which, we do let our normal leeway, and how's the development of the tool going? Next one is, how connected should the data centers be? Do we want IETA, and what's the framework for tying our data centers together? Somebody's looking for some data in permafrost. Should that search take them to, in a connected way, the data centers? Or should they be going straight into the Arctic data center and just doing a search? So we ask that. What's the role of the cloud? And I think we constantly ask that one. For the most part, if you ask the question about how much data we have in the Arctic data center, it's actually a lot. But putting it on the cloud, it's not that much. It's when you do the cost analysis and you do all the other analysis, most of the data can be extracted straight from the Arctic data center to your local machine, and then you can bring it, if you like, to a Google Earth Engine or whatever supercomputer you want to use. You can do that. It's different from remote sensing. It's different from having huge amounts of data that really we want to start thinking about what is the model of where the data goes. On the computing side, how do we integrate new techniques with our conceptual research models? And what I mean by that is mostly we fund process-oriented projects, and we know that, and that's where we'll stay, hypothesis-driven, process-oriented. But at the same time, machine learning is offering us something. It's offering us, I think, every day we find out that its predictability gets better and better. So what are the trade-offs here between these new statistical techniques and the way that we normally do our science? How do we engage our research community? Are we asking too much of our research community? And the Office of Advanced Cyberinfrastructure, they're constantly asking that question. How ready are your communities to do very big projects? So we're trying to assess that. And then what are the mechanisms of software adoption? How do we go about that? And I'll leave it there. It's